So the last topic in two-dimensional motion is centripetal force, which is what allows you to travel on circular paths. So the idea is that if you have an object that's traveling in any particular direction and you want it to curve, in order to get this object to bend this way, I have to have a force that's pulling it to the right. So at that place, there'd be a force pulling you this way, and then that would allow you to curve a little bit. But if you notice, once that curve has started, in order for you to continue curving, you need to be experiencing a force to the right, like so, which will allow you to keep curving. Let's see how my circle drawing skills are. But then in order to keep curving, you have to have a force pulling you directly to the right, and so on and so forth. So you notice that in order to pull this off, in order to get yourself to go around in a corner, there must be a force pulling you in towards the center of that circular path. And the name for that force is the centripetal force. So there are a few things that determine how strong a centripetal force you need. So we'll do F, C, C for centripetal. The first thing that matters is the heavier you are, the more force you need, obviously. I mean, that's true for everything. I'm gonna park an M on there. Next thing is the faster you're going, the more force you're going to need. And obviously, if something's going very quickly, you need to pull it harder to get it to bend in a circular path. So you need a V. And not only is it V, but it ends up being V squared. So your speed has a huge effect on how much force is required. The final thing is there's an R in the bottom. Now that's a tricky one to wrap your head around, but the bigger your R is, right? That means the bigger the circle is. That means the less curvature you need. Right? You're not curving as much because the circle is so big for you to go around. So the bigger the radius is, the smaller the centripetal force is required. All right. So this is one version of the centripetal force equation that uses your mass and your tangential velocity. So that's whatever speed you're traveling at any particular point in this path. It's called tangential is if this centripetal force stopped for whatever reason, you would stop traveling on a circular path and just continue traveling straight. As you, in whatever direction you happen to be pointing. You sort of get this experience when you're in a car and you travel around a tight curve. Your body is trying to go straight, so it doesn't want to turn. The only reason it does is that the tires are gripping the road, and then the tires are pulling on the car, and then the car is pulling on you, and as long as all three of those pulls are happening, you will get dragged around the corner as well. But you will experience that like shove towards the outside of the car while it's happening, because your body is trying to travel on a tangent. And if you aren't wearing your seatbelt and something catastrophic happens so that you become decoupled from the car, then you will travel on a straight line while it continues its curve this way. So buckle up. It's in your best interest. There is a second version of this centripetal force equation where I replace the speed with the distance that you're traveling, so the circumference of the circle, and the time it takes you for one full orbit. So it's more useful for something that spins at a particular rate, so something that you could quote in revolutions per minute, or if you're watching like an electron go around a proton or a planet go around a sun. Something that does the same path over and over and over again in a fixed amount of time. So to convert this version to that version, I'd have to realize that speed is the same as distance traveled over time. And if you travel around a circle, the distance you've traveled is the circumference of that circle, which is 2 pi r. And the time then isn't just an arbitrary time, it's the period of one full rotation. We're going to use a capital T there. Note that T is the time for a full rotation. Okay, now I have a v squared in this particular equation, so v squared then would be 2 squared is 4, pi squared is pi squared, r squared would be r squared, and t squared would be t squared. So if I replace v squared with this thing, I'd end up with centripetal force is m over r multiplied by 4 pi squared r squared over t squared. An r squared up here and an r in the bottom cancels one out, so I end up with centripetal force is 4 pi squared, the mass of the object traveling in the circular path, the radius of the circular path they're traveling on, and the time it takes squared. Alright, so you should be able to use either this version or this version to determine the amount of force required to keep an object on a circular path. And you just choose whichever one's convenient. If you're able to easily measure the speed of the object, then this is the one you use. If it's easier for you to know the radius of its path and the time it takes to complete one rotation, then you use this version. So if we were to try a question then, suppose on this particular pathway we have a 500 kilogram car, and that 500 kilogram car is trying to travel on a circular path that has a radius of 30 meters, and it is trying to get away with this at 50 kilometers per hour. Alright, so I have a mass, a radius, and a speed, so I'm going to use this particular version. As always, your speeds need to be in meters per second, so I'm going to have to do some conversion factors here. 50 kilometers per hour multiplied by, let's see, 1 hour is 60 minutes, and then 1 minute is 60 seconds, and there are 1,000 meters in 1 kilometer. So hours should cancel hours, minutes cancels minutes, leaving seconds behind. Kilometers divides kilometers, leaving me with 1,000. So if I had my calculator here, 50 divided by 60 is, 60 equals times 1,000 is 13.889 meters per second square. Meters per second. I say 13.889. Okay. So I have my speed in the correct units. Meters is the correct units, and kilograms is the correct units. So I start with my centripetal force formula, mv squared over r. So the centripetal force would be 500 times this crazy number up here, squared, and the radius is 30 meters. All right. So 13.88889 squared gives me 192.9 times 500 divided by 30 gives me 3,215.02. 3215.02. All right. So this car requires 3,215.02 newtons of force to the right in order to bend it around this circular path. And if it can't get that amount of force pulling it in, it will travel on a circle with a slightly larger radius. And that's fine as long as you're on a big flat tarmac surface like a parking lot. But if you're on a road where this path is a very narrowly defined strip of asphalt, traveling along an arc of a slightly larger radius means that your car ends up going like this, and at some point, probably about there, it leaves the road. And disaster ensues. So where is this force coming from? Well, the car is attached to the tires, and the tires are attached to the road. And the only thing that's making the tires stick to the road is the force of friction. So force of friction is mu multiplied by the normal force. And if we assume that this road is flat, then the normal force will be mu multiplied by the force of gravity. See, you've got your wheels turning. He said assuming the road is flat, meaning that maybe we'll be doing these problems where the road isn't flat, and we'll have to put this into components that are into more convenient reference frames, like bingo, but not quite yet. If I want to try and get this force shoved in here, so 3,215.02 newtons of force. I haven't been handed a coefficient of friction, but I was given a mass for the car. It's 500. And I do know that G is 9.8, assuming we're driving our car on Earth. So if I do 3215.02 and I divide it by 500 times 9.8, and I would get 0.656. So what I've got done here, and for those of you who are budding civil engineers, this is the kind of thing you're going to need to think about for the rest of your career, is if you want to have an on-ramp or a curve in a road with that radius, and you want cars to be able to travel on it at that speed, then the coefficient of friction between tires and the road cladding surface, so the asphalt or concrete or gravel or whatever you're going to use, has to be at least this. If it is not, then the friction from the tires will not be able to provide enough or a sufficient centripetal force in order to keep you on that circular arc. Now, fortunately, the coefficient of friction between rubber and asphalt is about 1.1, so no problem. But if you look it up for rubber on ice, like a polished ice surface, it is considerably less than this, which is why winter driving is so hazardous, because these curves that are engineered to be sufficient for this kind of speed work as long as it's tires on asphalt. As soon as it's tires on ice, this changes. You may not have sufficient centripetal force, and instead of going around the bend like you intended, you end up traveling on some other arc which does not line up with the roadway. Alright, so I'm going to erase this off. We're going to talk about fighter jets because they're fun, and then we'll see where we go from there. Alright, so this is not a hard fact, but people in general can't experience 10 G's of force for very long. That's 10 times the force of gravity before it starts to have deleterious effects on your health. So if you are standing vertical, for example, and you experience 10 times the force of gravity this way, your heart is no longer able to pump blood up to your brain. So the blood starts to pool in your feet. If you're lying on your back, the same thing happens, but instead of the blood going from your head to your toes, it goes from your nose to the back of your head. So your circulation system starts to fail around this amount of force. So if there's a maximum for the amount of centripetal force a human body can tolerate before they black out or suffer catastrophic systems failure, and you have people in machines that travel at speeds like 500 meters per second, when they turn at that speed, you're going to experience a centripetal force, and that centripetal force can't be bigger than this. If it is, you kill the pilot. And if the pilot dies mid-maneuver, then the jet crashes somewhere, and it's a disaster of billion-dollar proportions. So, if we were to just sort of draw out what's happening, got a plane going here at 500 meters per second, and it tries to pull one of these, turns around to go back from where it came. Well, that is going to require a centripetal force in order to pull that off. So I can start with my centripetal force equation, mv squared over r. And I'm going to put this 10 g's of force in for that centripetal force, because that's the biggest I can make it before I start to kill the pilot. So I have to think about what 10 g's would be. 10 g's is 10 times the force of gravity, which would be 10 times the mass of the pilot times 9.8. So I'm going to take that there, and I'm going to drop it in for my centripetal force. Now, you note that this mass is the mass of whatever object I'm trying to get around in the circle. It doesn't necessarily mean just the jet. The pilot needs to travel in that circle as well. So I'm going to worry myself just about the centripetal force needed to move the pilot in that circular path. And so if I do that, the masses on both sides of these end up dividing out, so they're not relevant. I have a speed, so I end up with 10, g is 9.8, v would be 500 squared divided by r. So I'm going to pop the r up here. I'm going to put these underneath, and I'm going to calculate this. So 500 squared be 250,000 divided by 10 divided by 9.8 gives me 2,551.02. meters. So if you're traveling in a plane that fast and you want to not kill yourself when you execute this turnaround maneuver, you have to pilot the craft so that the radius of this path is about 2,550 meters. That's 2.5 kilometers. And that's just a radius. That means that the distance, right, from here to here, right, the horizontal drift you're going to have as your plane tries to turn around ends up being greater than 5 kilometers. That's quite a bit of land to cover just to turn your plane around. And Mach 1.5 is, I mean, that is fast, but I don't think as far as fighter jets are concerned, that's not maximum velocity. So when you've got planes traveling at those sorts of speeds, in order to not kill the pilots, they have to take these crazy long radii. So next time you're watching a Top Gun film and they have all sorts of close plane encounters, keep that in mind, that that after they make one pass at each other, they then have to travel on an arc that is almost 5 kilometers in radius just to turn around for the second pass. One thing you can count on in physics, that we are going to ruin every single movie you ever loved, so no problem. So that's the basics of this this idea, is that you are either going to put in a force, a mass, and a speed and calculate an R, or maybe you're going to have 3 numbers and get a speed, or maybe you're going to have 3 numbers and there's some sort of limiting force that you can apply measured in G's that you can calculate. So you should be able to handle the practice problems.